So in 6.2 and 6.3, we're going to be looking at the normal probability distributions. And specifically, we're going to be given different scores. We need to be able to go from a z score to a percentage. And that would be in 6.2. A percentage to a z score, also in 6.2. And then in 6.3, you're going to add just one step to this, where they're going to give us an x. We turn that x to a z score, which then we can turn into a percentage. And vice versa, I can go from a percentage to a z score, and then back to the x. That's also in 6.3. We've done this before with the empirical rule. But the idea is now we're going to be dealing with more complicated numbers, so we're going to be using the technology to do that. In Chapter 5, everything was discrete. Like whole numbers, right? You could say what's the probability of getting 5 answers right, 6 answers right. It's not 3.5. These were all whole numbers. And each of those outcomes was assigned a probability. Probabilities added to 1. Our histogram, we had just a bunch of little rectangles, and we could add up the areas to equal 1. So that's Chapter 5. Everything we just did on binomial, that's discrete. You have a set number, and our outcomes have to be whole numbers, right? Well, in Chapter 6, what we're going to be doing is looking at continuous random variables. So a couple ways of doing this, but we call it a density curve. The idea is that the total area under this curve is 1, and if I was to literally calculate the area, it would all add up to 1. Okay. Specifically, we'll be looking mostly at a normal distribution. So normal distribution is a type of density curve. Okay. So you would have your normal distribution, right? And if it was normal, down in the center would be the mean. And then what we've done is we've split that up into 1, 2, 3 sections. 1, 2, 3 sections. This first one would be the mean plus 1 standard deviation, mean plus 2 standard deviations, and mean plus 3 standard deviations. Going to the left, mean minus 1 standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. And we've done from before using the empirical rule, also known as the 68, 95, 99.7 rule, that within 1 standard deviation of the mean is approximately 68% of the data. Within 2 standard deviations of the mean is approximately 95% of the data. And within 3 standard deviations is approximately 997. So what we're going to be able to do is we're going to take these are all basically x values, and we're going to standardize them. So when I do a standard normal distribution, then that is going to be, instead of x values, we're going to be looking at z scores. When we standardize it, the mean has a z-score of 0. And then as I go to the right, 1 standard deviation would be 1, 2 would be 2, 3 would be 3, and over here we would have negative z-scores. So these would be our standardized normal distribution. Still bell-shaped, but now we have these standard numbers that stand for the mean and standard deviations. Okay. So here's what we're going to do. Assuming women's height are normally distributed with a mean of 63.6 and standard deviation of 2.5, find the probability women's height is between 62 and 66 inches. So we're going to start by drawing out the picture. And in the center would be the mean, which happens to be 63.6. Now if I go to the right of that, that would be the mean plus 1 standard deviation. So 63.6 plus standard deviation of 2.5. So that would give us to, what is that, 66.1? Now I can also go to the left of that, would be the mean minus 1 standard deviation, so 63.6 minus 2.5 would give us, what is that, 61.1. So we want between 62 and 66. Those are not exact values this time. Those are not exact z-scores. 66 is more like right in front of this 66.1. And then 62 would be between the 61 and the 63, so somewhere in between those two would be the next value of 62. And what we want is we want the area between these curves. I know using the empirical rule, and this is one of the reasons that we have the empirical rule, that within one standard deviation is 68% of the data. Both of these are less than one standard deviation away. So I know using the empirical rule that if I brought this in, that this will be a percentage less than 68%. Pretty close, you know, it's not like that far off, but probably between 50 and 68%. Okay? So we've cut off these pieces, so our area is going to be reduced less than 68%. That's just the logic behind it. Okay? So what we're going to do is we're going to find the probability that a woman's height is between 62 and 66. Our first thing is going to be take this x and turn it into a z. How? Well, the formula for z. The number minus the mean divided by the standard deviation. So this number 66 minus the mean divided by the standard deviation 2.5. Same on this one, our x is 62 minus 63.6 all over 2.5. So 62 minus, make sure I did that right, 63.6 divided by 2.5. So that would be my lower z-score. And the other one was, I think it was 66. I'll double check. Yep. So 0.96. So basically, we're going between negative 0.64 and 0.96. This question that we're doing right here is actually a 6-3 question. This right here would be what a 6-3 question looks like. When we've turned it into a z-score, that is actually what a 6-2 question is going to look like. So in 6-2, they have you just go, they'll give you the z-scores and they want the percentage for that. In 6-3, they're going to give us the x's, which we can turn to z's and then find them. How would I do that now? Well, when it was a binomial distribution, we used binom CDF. This is a normal distribution, so let's go ahead and look in the calculator. Under Menu, Statistics, Distributions. Like I said, we did binomial PDF and CDF for the binomial. Here I'm dealing with a normal distribution, so it'll be normal CDF. We don't use normal PDF because we want we're not doing exact values. We're doing CDF. We always have to have a range with a continuous, so we're going to use norm CDF. So we will use normal CDF, min, max, mean, standard deviation. So for this one, it would be norm CDF. Our minimum was this lower z-score of negative 0.64. Our maximum was 0.96. Our mean, and don't put in the 63.6 because this is basically the mean of a z-score. So the mean of the z-scores, I wrote this picture, when I'm dealing with z-scores, the mean is 0 and one standard deviation is worth 1. So put a 0 and a 1. That's only for z-scores. The mean is 0, the standard deviation is 1. So the lower bound was the negative 0.64, the upper bound was 0.96, Notice it defaults 0 and 1. That's if you're putting in a z-score. If I hit OK, here's my percentage. What did I say? I thought it would be between 50 and 68%. That was pretty close, so about 57%. I will expect you to be able to do all of this on the test. I'll expect you to know how to turn an X into a z-score, and I'll also expect you to turn that z-score into a percentage. Okay? But in 6.2, all you're doing is getting a z-score, using the command, and finding a percentage. In 6.3, you have an X, and I want a percentage. Well, here's the good news. I can still use normal CDF. So I'm going to keep doing these both ways just so we can see, but I can actually put in the minimum X, which was 62, the maximum X, which was 66, and this time I put in the actual mean and the actual standard deviation. Since we're not dealing with the z-scores, the mean is going to be 63.6, and the standard deviation is going to be 2.5. So I can run statistics, distributions, norm CDF, and go between 62 and 66 inches tall with a mean of and a standard deviation of 2.5. Okay. Should give me the same percentage. So when I'm doing these, I can actually go straight from the X to the percentage. You just have to make sure you fill in the actual mean and the actual standard deviation. Okay. I still recommend you practicing turning it into a z-score just because that helps us understand the visual with the empirical rule, or drawing it out just so you can see. If I ran this and I made a mistake in here, and let's say I did 0.25, this would be like 99%. And be like, wait a second, this doesn't look like we shaded 99%. So drawing the picture or turning it into z-scores really helps understand what the percentage is. So I encourage you to do that. Assuming men's heights are normally distributed with a mean of 69 and a standard deviation of 3.7. What is standard casket has an inside length of 75. That's kind of uncomfortable. What percent of men are too tall to fit in a standard casket? Well, too tall means I want the probability of your height being greater than the average. Greater than the height of the casket, which is, that means what? They're going to have to lean you over and bend your knees. You're going to be too tall to fit in the standard casket. Or pony up for a nice one, right? So I can do this, but this time I'm doing greater than 75. Let's draw the picture out. Our mean is 69. If I go one standard deviation to the right, 69 plus 3.7 should be 72.7. You still haven't reached 75, so I'm going to go again. Another 3.7. This one was 69 plus 3.7. This would be 69 plus 2 times 3.7, or we add that twice to give us, what would that be, 75, 76.4. So now we're getting close to 75. 75 is going to be somewhere in between these two. And we're finding the area to the right of that. I can go, if this is a 6.3 question, and go straight to norm CDF. My minimum, right here, the lowest point we get, is a height of 75. My max, we shade to the right forever. So we would put an infinity there. Or, if you don't have the CAS calculator, your infinity will freak out, so just put a bunch of 9s. Comma, mean, comma, standard deviation. just looking at this, once again, using the empirical rule, I can say, all right, I know this was 34%, I know this is 13.5%, 68, 95. This is probably going to be less than, I don't know, between maybe 3 and 5%. 68, 95, so this is like 2.5% plus a little more. I don't know, between 3 and 5%. It's an approximation. But the idea is that if you run this wrong, you get an answer like 96%. That should stop you. You know, that didn't look like I shaded 96%. So either use the picture or use the empirical rule to kind of figure out what should the answer be approximately. So now we're going to run statistics, distributions, norm, CDF. Our lower bound was the height of 75 inches. The height, or if you have infinity, use an infinity. Make sure I'm not doing this wrong. 75, yep, 69 and 3.7. So 69, 3.7. No, about 5%. Like my approximation was a little off. So 0.052. And that would be the probability of having basically a casket that is not tall enough for you, or you being too tall for the casket. Okay? Another option. You should be able to turn this into a z-score. 75 minus the mean, divided by the standard deviation. 75 minus the mean, divided by the standard deviation. About 1.6216. See, I can run norm CDF on that z-score. Now my minimum would be that 1.6216. My maximum would still be infinity. But my mean, the mean of a z-score, would be 0. The mean of a standard normal distribution would be 0. And the standard deviation would be 1. So when I go to run this, stat, distributions, norm CDF, 1.62, make sure you get a little more on there, 1.6, upper bound, and mean standard deviation, leave that alone. Is the answer the same? Well, there's a little round off there at the end. Within 3 decimal places, we're doing fine. You need to know how to do both of these, but keep in mind, in 6.2, they're going to give you the z-score and have you find the percentage. In 6.3, you're going to be given an x and find a percentage. You need to be able to get the same answer either way. IQ scores are normally distributed with a mean of 100, standard deviation of 15. Find the probability an adult chosen at random has an IQ between 110 and 120. Okay, so let's go ahead and start with probability of your IQ being between 110 120. If I'm doing this from the x's, norm, CDF, our minimum, our maximum, our mean, and our standard deviation. If I'm doing it from a z, I've got to take each of these minus the mean divided by the standard deviation. This would be 2/3 or 0.666. And this would be so 20 over 15 1.333. And that would no longer be an x. We just converted those into z-scores. Double check that. By 666. I messed that up. Let me double check that. Yeah, it should be 110 minus 100. That's why. Divided by 15. There we go. And then 120 minus 100. Group those, divide by 15. 1.333. Okay. So, menu, statistics, norm CDF. If I'm doing the x's, we went from 100 to 120 with a mean of 110 and a standard deviation. We went from 110 to 120 with a mean of 100 and a standard deviation of 15. Okay, I feel good about that. Or we went from 2 as a z-score, so leaving 0 and 1, and our answers are pretty dang similar, right? 0.161, 0.161. Okay. This one, it says IQ less than 95. Norm CDF. What's my minimum? If you're not sure, then you should be stopping and drawing these out. Okay? Because this one was easy to say, okay, the mean's 100. Then it'd be 115. Then it'd be 130. And I can see between like 110 and 120. And that was our percentage. It was about 16%. But this we're saying, with a mean of 100, well, 95 would be back here. This would be 85, actually, so 95 would be closer to here. And less than would be everything to the left of that. So what would our minimum be? Well, left forever, or negative infinity, or negative bunch of nines. Comma, maximum, comma, mean. My maximum was not 100. Maximum of, what was it, 95? With a mean of 100 and a standard deviation of 15. Or 95 minus 100 over 15. That's negative 1/3. So that would be norm CDF. Still negative, bunch of nines, but up to negative 0.333 with a 0 and a 1. Either way, let's see. Statistics, distributions. Negative infinity, I'm going to leave that alone. You could put negative 99999 and do the same thing. Our upper bound, we were going to a score of 95 with a mean of 100 and a standard deviation of 15. Or leave that alone. Upper bound of leave that alone. Oh my goodness. Upper bound of, geez, what was it, negative point with a mean of 0 and 1, and about 36.9%. So either way, we get an area of 0.369. Okay? All right, so that's basically it. For the first half of 6.2 and 6.3, they're going to give you scores and ask you to get a percentage. What we're going to finish this with now is what happens if they give me a percentage and they want a score. Okay? So we're going to be using the same kind of sets of data, but they're going to be giving me a percentage and they want a score. So when they say P of 60 here, what we do is, we'll just make sure we're clear. When I'm going from a z-score to a percentage, or an x-score to a percentage, what we did on the top is we used the command norm CDF with a min, max, mean, and standard deviation, right? That would be going from a z-score to a percentage. What we're doing here at the end is we're going to be going from a percentage to a z, or a percentage to an x. And so the command, instead of norm CDF, since we're going the opposite direction, is going to be inverse norm. It's not helpful. Try that again. Inverse norm. Now the trick with this is it always that we're going to put in our percentage as a decimal, but it's always to the left. The inverse norm only does the area to the left, and then we can fill in the mean and the standard deviation. Okay? Well, we're going to start with a question where they give us the percentage to the left, so that's not a problem. So let's start with this. If I wanted P of 60, I can go from that. That basically means the 60th percentile. That means the left 60%. Now notice they also said that does also mean the top 40%. So these two mean the same thing. Well, if I want a z-score for that, then what I can do is I can use inverse norm. The percentage to the left would be 0.6. If I'm doing a z-score, the mean is 0, standard deviation is 1. And this would give me the 60th percentile. So under menu, statistics, distributions, here's my norm CDF. Right below it is inverse. They want the area, that's the percentage to the left. Put in 0.6 and hit OK. This right here, 0.2533, does not mean 25%. That is utterly ridiculous. Okay? What we just got was not a percentage. We were given a percentage. This is a z-score. That basically means that the 60th percentile is 0.2533 standard deviations above the mean. That would give us the 60th percentile. That 0.25 is not a percentage. If I ask you for a z-score and you turn this decimal into a percentage, we're going to have a problem. A z-score is not a percentage. Well, in 6.3, what they're going to want is they're going to actually want the actual IQ that does this. Well, there's a couple options. I could take the formula for z, and I can fill in what we know. We just figured out the z-score is equal to, we don't know the x this time. That's the score we're finding. We want the x value. So leave that blank. But we know the mean, and we know the standard deviation of IQ, because that was on a previous question. The mean was 100, standard deviation was 15. So I'll use that 100 and that 15, and I can solve this for x by first multiplying by the 15, and then adding 100 to that. So taking that 0.2533 and multiplying it by 100, no. Multiplying it by the standard deviation, which was 15, about to make myself a liar, and then take that result and add 100, 103.8. So that's an option. The other option is I can actually go straight to an x by using inverse norm. Same percentage, 0.6, but fill in the actual mean and the actual standard deviation. So the actual mean was 100. The actual standard deviation was 15. And so if I go to my inverse norm, and instead of 0, 1, I use the actual mean and the actual standard deviation, then it will go straight to the x. That's good that you can do that, but just understand what your calculator is doing. Okay? Basically, it is taking the time, 103.8, there we go. It's taking this percentage, turning it into a z-score, and then it's running through the algebra to figure out what the x is. So it's doing all of that for you. And I'm totally fine if you want to use your calculator to do that. Okay, a couple more examples. Find men's height separating the top 10%. Let's start with 6'2". If I just wanted the z-score, inverse norm, what's my percentage? I'll give you a hint. It's not 10, because the top 10%, right, means this top 10. But inverse norm always wants the area to the left. So what you have to do is you have to go, well, the top 10% is the same thing as 1 minus that percentage, or 0.9. If I have 10% on the right, that means I have 90% on the left. The top 10% is the same thing as the lower 90%. Comma 0, 1 for a z-score. I'm just going to change this to 0.9, comma 0, comma 1, 1.28155. That is not a percentage. Do not tell me 128%. That is a z-score. That means 1.28 standard deviations above the mean gives us the 90th percentile, or the top 10%. If I wanted an x, I can now take z is equal to x minus the mean divided by the standard deviation. Where did I get these numbers? Well, men's height was right here. The mean is 69 and the standard deviation of, I messed up there, 3.7. My memory's not good as I thought. And then I could solve this. Multiply the 3.7 up, add the 69, or I can use inverse norm of the 0.9 and fill in the actual mean and the actual standard deviation. Menu, statistics, distributions, inverse norm. Top 10% is the lower 90%, mean of 69 inches, and 3.7. And that would be the same thing as taking this number, timesing it by the standard deviation, and adding the mean over. So either way you do it, you should get 73.74. And last but not least, birth weights in Norway, normally distributed with a mean of 3,570 grams. Keep in mind that's grams, we're not talking pounds, not big old fat babies, with a standard deviation of 500. If a hospital plans to set up a special observation for the lightest 2% of the babies, right, what weight should we use? At what weight do we bring that person in because they're going to be at high risk? They're the lightest 2%, right? The lightest 2% is going to be this bottom 2%. So how would I do that? My percentage to the left, my mean, my standard deviation. Inverse norm. The lightest 2% of the babies with a mean of 3,500 and a standard deviation of, I think it was 500. 3,570. So let's go back and change that to a 70. Okay. 2,543.13. So anyone less than that, this would be the lightest 2% of the babies. The only other thing that we'll do sometimes, and I do this just to be a little tricky, is I would say something like, what about the middle 60%? So if I want the middle 60%, then basically I'm going to say, well, here's the middle, and I want 60% off that middle, right? So what you would do is I could do, by the way, I'm going to have two values here, either two z's or two x's. So I need to find inverse norm and to find the first one, I'm going to put in 50% plus our percentage divided by 2. So inverse norm of 0.5 plus half of that 60 would be 0.8, comma, mean, standard deviation. So if I'm doing a z-score, it'd just be 0 and 1. That's going to give me my highest percent. Why? Well, the middle, the mean, represents 50%. So if this right here is 50% of the data, then what percentage to the left is this, right? Well, it'd be that 50 plus 30 of it. What percentage would this be? 50 minus the 30 of it. So the second one is going to be 0.5 minus the percentage over 2. So it would be 0.5 minus 0.3, or 20%. And what I'm doing is if I figure out between 20% and 80%, that represents the middle 60%. So I know this is a little tricky, but just you've been warned, I'm going to have a couple questions like this on the quiz. Okay? So how would we do that again? Inverse norm, what was it, 0.2? And inverse norm, 0.8. Notice those are opposite. They should be with z-scores. Negative 0.842 and positive 8.2. The first one actually would have been the positive. And those two z-scores would be the middle 60%. They're symmetric around the mean, and they would have 60% in the middle. I can check this just for fun and giggles. I could take these two scores, call that my min, that my max, and I could do norm CDF. With the negative as my lower, and the positive as my upper, and this should represent mean of 0, standard deviation of 1 is the middle 60% of the data. Okay, so I know that one's a little trickier, but I will have a couple questions like that. Mostly what you're going to be dealing with the homework is the top percent, bottom percent, going to z-scores and going to x values. So make sure you got that. Shouldn't be terribly hard. Keep it up.